Good afternoon, everyone. Can you hear me? Okay, excellent. Thank you. Okay, so in keeping with the theme this semester of providing you a taste of a variety of different topics that relate to systems engineering, today we'll be continuing the lecture on digital semiconductor technology and CMOS logic. I'm going to try to get to some signal integrity as well. I'm going to try. So last time, oh, by the way, quiz, I published quiz 6, and you'll have, that'll be due a week from today before class next Monday. So if you, I'll give you some time at the end to take a look at that. So last time we introduced this topic, and I started out by explaining how semiconductors work. So you start out with a silicon lattice, which is a crystal where you've got atoms that are arranged with covalent bonds with 4 of their neighbors at various angles, and has very poor conductivity, but you can add a dopant into the mix, into the structure, the crystal structure, which replaces some of the silicon atoms with atoms from either group 3 in the periodic table, column 3, or in column 5. If it's a column 3 element like boron or gallium, then that will create p-type silicon, and it's named p-type. P stands for positive, and that's because that'll end up giving you charge carriers that are holes or lack of an electron in the structure of the crystal. So that's p-type, and then n-type silicon is formed when you dope the silicon structure with an element from group 5 or column 5 in the periodic table, such as phosphorus or arsenic, and that will give you n-type silicon, which has electrons that can move around and serve as charge carriers. So charge carriers make the semiconductor more conductive. And also, if you put together p-type and n-type silicon together, you kind of push them up against each other, it creates a diode that will only conduct current from the p-type to the n-type, which is referred to as a forward bias. And that's also happens when, that'll happen when the p-type side, the anode, has a positive voltage relative to the cathode, which is the n-type. So current flows from P to N, and current will flow depending on, in order to get current to flow, even in a forward bias, you need to have the positive voltage on the P-type relative to the N-type. So that's a diode, and then if you try to reverse bias it, like you have the P-type has a negative voltage relative to the N-type, that's a reverse bias, and the diode will not actually conduct any current because the charge carriers, it causes the charge carriers in both the P and the N-type silicon to move away from the junction where they meet. So because they move apart, no current, the charge carriers won't send current between the two, right? So that's a reverse bias. So so that's a diode. How about a transistor? Transistors are formed, can be formed in silicon, but it's a little tricky to get the hang of because they're more complex than a diode, and they're a 3-dimensional structure. So the picture I'm showing there is a cross section, which is kind of like if you took a chip and cut it, and you looked at the side, the edge where you cut through. Kind of like looking at, like if you have a sandwich, you cut a sandwich in half, and then you look at the middle of the sandwich where you cut it, right? A cross-sectional view. And basically, you have a substrate which generally is going to be a p-type silicon, but it's usually lightly doped p-type silicon. And then you have these two things called diffusion areas, which are the opposite type of semiconductor, the N type. And then they are separated by a small amount of space. In fact, if you guys ever heard of like semiconductor technology is often, or actually I should say, semiconductor fabrication process is typically named after the length of the channel. So the distance between the two diffusion areas there, between the two, the two diffusion areas, that's what you would call, that's how you would name this technology that you're making these transistors in. So you might have heard that Intel has this God, what are they at now? Okay, so they're at 22 nanometers. So there's right now there's a version, they have a version of their fabrication that can build these transistors with a 22 nanometer spacing between the two diffusion areas. And they're trying to spin up production on their 14 nanometer. I think they make some chips in 14 nanometer already, but they want to move all of their chips to 14 nanometer. So that 14 nanometers refers to the distance between the two diffusion areas, which are the source and the drain. So that's going to be, like when you make a chip, that's going to be the smallest feature size is going to be the distance between the two diffusion areas. And then above that distance is where you have your gate, and the gate is separated from that area in between using a glass, silicon dioxide. And the silicon dioxide is an insulator. So you might think, well, wait a minute. I mean, that's pretty small. Like, what are we like? What is this? What is this relative to? Well, the silicon has a atom spacing, an atomic spacing of about a half a nanometer. It's 0.543 nanometers. And then the cell size, which is the kind of the smallest unit of repetition inside the lattice, inside the crystal, is 5 nanometers. So once you get down to 5 nanometers, you're only going to have enough room in there for one unit cell. And then once you get less than a half a nanometer, you're basically smaller than the distance between atoms. So you can't really go any smaller than 0.5. So we're basically at 11 nanometers as compared to about 0.5. So we're about 22 atomic widths at this point. But you can imagine that, obviously you can't continue shrinking that indefinitely because, you're limited by the atomic size, the atomic width. So, but basically, yeah, so this creates a transistor, a MOSFET transistor. It stands for metal oxide silicon semiconductor. Metal is referring to the gate, but it's actually not made out of metal. It's made out of polysilicon. I think they have some that are made out of metal, but when these things were named, the gate was metal, so that was the gate. And then oxide is glass. Silicon dioxide is just regular glass. And then semiconductor would be then the body of the transistor, or the substrate, which is referred to as a semiconductor because it is not only pure crystal silicon, but it also is doped. If you have silicon that's not doped, I don't believe that's referred to as a semiconductor. Maybe it would be, but it would be, no one uses pure silicon for anything, as far as I know. It only becomes useful when you dope it, because doping it allows you to change the conduction characteristics. So these guys are the glass industry would like a word with you. Well, glass is silicon dioxide, so that's not pure silicon. Pure silicon's a crystal. Glass is not a crystal. As a matter of fact, when you make glass, your goal is to avoid having any part of it crystallize, because that's bad. And when you're it's not good for glass. You don't want glass to be crystal. So glass is when it's made, it's deliberately made to avoid crystal formation. Because if you have crystal, like if your cell phone screen had any crystal in it, then it wouldn't be a very good screen. It wouldn't be very durable. So yeah, pure silicon crystal doesn't occur in nature either, I don't think. You have to make that. If you go to the beach, you know, and you see the sand on the beach, that's actually silicon dioxide. That's basically kind of glass, small bits of glass, essentially. Pure silicon, growing pure silicon is an energy-intensive process. Okay, so yeah, so that's right. So this gives you a MOSFET transistor, and it basically gives you 4 terminals. There's the gate, which is in the middle, and then there's the source and the drain, and then there's the bulk terminal, which is the substrate. And so those are 4 terminals, and it's very, now even though you typically see a transistor only depicted with 3 terminals, the 4th terminal is wildly important. It's just usually not shown because it's usually implicit. But the 4th terminal is hugely important because if you don't hook up the 4th terminal right, your chip is going to fry. And it will release the magic smoke, as Charles would say. So the 4th terminal is super important. In the case of and the reason is because of latch up. So you want to make sure that if you have an N-type transistor like the one I'm showing here, the substrate needs to be grounded, and it needs to be hard grounded. You want lots of connections to ground there, because that way, if you keep the voltage of the substrate at ground, it guarantees that you're not going to have any current going from the source into the substrate or vice versa, because the substrate in the diffusion area forms a diode. And remember, I said that the current can only go from P to N, and only then if the voltage potential of the P side is higher than the N. Well, if you have a substrate and you ground it, then that guarantees that these guys are electrically isolated. However, they do still form a capacitor, these diffusion areas in the substrate, and I'll talk more about that later. But you're not going to have current exchanged. Okay, so there's 4 terminals: substrate, source, drain, gate. You'll notice that this structure is symmetric. So the source and the drain it doesn't really matter which one you call source and drain. Although typically with nMOS, the source by convention is the terminal at the lower voltage. And in the PMOS, it's the opposite. Source is at the higher voltage. But the source and the drain functionally are equivalent. You know, when it comes to naming which one is the source and which one is the drain, is that comes down to a convention. Okay, so here's another picture on the left. Okay, so first of all, this is an nMOS transistor. Why? Why is it nMOS? Well, it's an nMOS because the diffusion areas are N. And that's the source and drain, or the diffusion areas. If the diffusion areas were P, the body would then have to be N, so it would have to be switched, and that would be a PMOS. But this is an nMOS, and again, N is because of the diffusion areas. Now you'll notice here that this says N+. It doesn't say N+ on this picture, but the diffusion areas are labeled N+. Why is that? That's because N+ means it's highly doped. So the source and the drain are usually highly doped versions of the silicon, meaning that there's more dopants. There's literally just more of the silicon atoms have been replaced by the dopant atoms. That's all that highly doped means. The gate and the body, or the gate and the substrate, you know, body is the kind of the name of the term of the 4th terminal, whereas the substrate is kind of like when if you're talking about a chip, the substrate is the body is the substrate of the transistors. But anyway, the gate and the body form a capacitor. The reason is because you've got a conductor separated by a non-conductor, a dielectric separated by a conductor, and this forms the gate forms a capacitor, and you want that. You want that. So now if you look at, here's another picture on the right. So part of the problem with this picture on the left is you're only seeing 2 dimensions. These are 3-dimensional structures. So I mentioned that the space between the 2 diffusion areas is typically the smallest feature size. It's the smallest unit of length that you can achieve in your given fabrication technology. However, and that's referred to as the length. So that's called the channel length. And you want that channel length as small as can be, because that determines the switching speed of the transistor. But there's also the width, right? So you want the width. Width is is kind of how deep the transistor is, right? And the width also determines how fast the transistor switches, and also determines how much current is passed from source to drain. So that's the width and the length. Now the width, as I mentioned, is usually a constant. So if it's Intel's 11, or say you're in Intel's, you know, a 14 nanometer technology, then the length is always going to be pretty much the length of every transistor is going to be just that. It's going to be 14 nanometers. But the width is something that you can vary. The width, the minimum width, is typically twice the length for an nMOS and 4 times the length for a PMOS. But you can make the width bigger if you need a stronger transistor. So that width is your transistor strength. And so you can make it deliberately bigger, and this is the way you can get a more powerful transistor, as you can scale up the width beyond whatever the minimum width is, which is, again, is, like I said, it's usually twice the length. And then there's this oxide thickness, which is the thickness between the gate and the channel, and you want that to be as small as possible. And so fabrication processes shrink that. That's one of the other things they shrink along with the channel width. Okay. So basically the way this thing works is that if this is an nMOS, which it is, we can tell because there's N is the source and drain. You have PMOS is the bulk, or is the substrate, or is the body of the transistor. There's a lot of terms for that. And those have P-type, so it has the positive charge carriers, the holes, right? And then you ground it. It's important to ground that body. But if you charge up the gate, and you put a voltage on the gate, that'll basically create a capacitive effect where you'll accumulate charge on that gate. And that does this thing where it attracts the minority charge carriers into the channel. And so even though this is P-type silicon, it has both holes and electrons. The holes are the majority charge carriers, the electrons are the minority charge carriers. Now, I think this is also the reason why you only lightly dope the substrate. I think if the substrate was like a P+, then it would be harder to get these minority charge carriers. But this is just regular P-typed, lightly doped P-type silicon. It still has electrons in it, and those will get attracted here to the channel whenever you charge up the gate. So the capacitive effect of the gate, when you put a positive charge on the gate, you attract minority charge carriers. Okay. Now, and then once you do that, you have electrons in the channel, and those will then conduct electricity between the source and drain, because of course the source and drain also have electron charge carriers, right? So basically, this becomes an electric. You could think of it as an electric, as a voltage-controlled switch, where you basically, if the gate is at ground or 0, Boolean or logic 0, then the source and drain are cut off from one another. But if the gate is at 1, logic 1, or you put it at VDD, positive voltage, then the gate turns on, and it connects the source and drain. And that's pretty much how you can think of it. That's the simple way to think of it, as a kind of a switch, right? It's either on or off. If it's off, then the source and drain are disconnected. If it's on, they're connected, and that's controlled by the voltage at the gate. Okay. Now the problem is, and this is where things get confusing, I think. The gate is a capacitor, right? And so obviously the top plate is just connected to a wire, controls the transistor, right? The bottom of the capacitor, that's the part that's weird, because when the transistor is off, the bottom part of the capacitor is the substrate, right? But when the gate is on, the bottom part of the capacitor is no longer the substrate. It's no longer at the substrate's potential, right? What ends up happening is that the voltage of the substrate is at ground when the transistor is off. But when the transistor is on and you start sending current between the source and drain, the voltage of the channel changes. It's no longer ground. In fact, what happens is that the channel voltage becomes the average voltage of the source and drain. Why? Because the channel becomes something different when the transistor is on. It becomes a conduit between the source and drain. And so the voltage between the gate and the channel is going to depend on the source and the drain voltage, or the voltage between them, right? So it's no longer a capacitor relative to ground. It's a capacitor relative to whatever's going through the channel. That's the part. That's a very subtle point, but that's a very important aspect of how MOSFET transistors work. And I'll come back to that in a minute. So PMOS, or PFET, or P-type transistor, whatever you want to call it, the P-type transistor is just like the N-type, but the types of the doping is switched. So the source and the drain, which again are the two diffusion areas, are P-type, and then the substrate is N-type. Now the problem here, the thing that's kind of confusing, I think, about the PMOS is that you can think of it like it's kind of works logically. It works the opposite way, because in order to turn a PMOS transistor on, or a P-type transistor, you basically ground the gate. You put the gate at logic level 0, and that will turn it on, and anything above that will basically, well, not anything, but basically logic level 1 turns it off, logic level 0 turns it on, right? But that's not actually what's happening. What's really happening is that because the substrate is of the opposite type, we don't ground the substrate. We have to connect the substrate to VDD. So we charge up the substrate to VDD. That ensures that we want the substrate to be the highest possible voltage we can get in this chip, and that way we know that the substrate will be reversed biased relative to the diffusion area. That means we don't want any current going from the substrate into the source and drain. So the substrate is at VDD, which means that when you start putting you take the gate and you start lowering the voltage of the gate relative to VDD, what that actually looks like is a negative voltage. So what you end up with is, what's really happening with a PMOS is that PMOS and nMOS work the same, except the gate is actually what causes it to turn on is a negative gate, essentially, negative threshold. So if your threshold, there's a threshold voltage that basically delineates between gate off and gate on, and that voltage is usually about 700 millivolts, 0.7 volts. So in the case of an nMOS, if the gate is at 0.7 volts relative to ground, the gate will start to turn on. And if it's a PMOS, it's negative 0.7 volts, right? Now, when you're designing your digital logic circuit, you don't think of it as a negative voltage. You think of it as, logic 0. It's not really logic 0, though. It's actually just negative, any kind of a negative voltage you put on the gate is what's going to try to turn the transistor on. So that's really what's happening there. And that gets a little, to me, that part was always a little confusing. So people like to think of a PMOS as you put a 0 on the gate, turns it on, but in reality, you're putting a negative voltage on the gate to turn it on. Okay, so this slide is showing these gates kind of like using the switch model. So with an nMOS, if the gate is 0, you turn it off. With a PMOS, if the gate is 0, you turn it on. And with an nMOS, if the gate is 1, you turn it on. And with a PMOS, if the gate is 1, you turn it off, right? So logically, they work the opposite, okay? So now you might be saying, wait a second, how do we build these things in the same substrate? Well, I found this picture, which actually shows it pretty well, I think. So the nMOS, most chips have a P-type substrate. So the nMOS diffusion areas are just stuck straight into they're just injected straight into the substrate, all right? But the PMOS has to have an N-type substrate. So they use this thing called a well, where you actually put a real big diffusion area that goes deeper, and that's your N well. And then inside the N well, that serves as kind of a little local substrate, which then you can put P-type diffusion areas to create the source and drain. And that's exactly what it looks like when you design a chip. You have to literally put these wells in. Now you might say, what is this extra thing over here? Like in the NMOS, why do you have a, this P plus here? This is the way that you connect the substrate to ground. So generally, you'll have this little diffusion area here that is connected to ground through a wire, and this way, in order to get a good electrical connection to the substrate, you have to pass it through highly doped P-type and then into the lightly doped. So this kind of just serves as this diffusion area here just serves as a gateway to get a good contact into the substrate. And the same thing applies over to the end well. So to get the end well connected to a wire, basically, which is going to be your VDD, your power supply, you don't want to go straight from metal into end well, because the end well it's not very conductive because it's not doped very highly. But if you have this highly doped N-type silicon that serves as an interface between VDD, metal wire down through a via, connects to the highly doped N, and then that transitions down to the lightly doped N. That's generally how these transistors are designed. That part's not as important. That's only important if you're actually doing layout, and we're not going to talk about layout in this course. But I just want to point that out because it's in this diagram. Okay, so now once you have the transistors, how do you build gates? So gates are typically, CMOS logic anyway, is complementary metal oxide semiconductor. It means it's complementary because basically you have one PMOS and one matching NMOS for each input into your gate. And so the NMOS, the PMOS is the part of the gate that's going to connect the output to VDD if the output of your gate is 1. And the NMOS transistors are the part that are going to connect your output to ground if the output of the gate happens to be 0. Now only the pull-up network and the pull-down network are only one of these is supposed to be on at a time. So your output is either going to be connected to VDD or ground depending on the inputs. So you'll notice that the output is actually wired in, basically just wired in between the pull-up and the pull-down network. And then the inputs are fanned out to both. So each input is connected to one PMOS transistor and one nMOS transistor. So the total number of transistors is simply 2 times the number of inputs. So if you have a 4-input gate, you'd have 8 total transistors. You'd have 4 in the PMOS pull-up network and 4 in the nMOS pull-down network. So why are they built like that? Okay, so a couple things. So first of all, the fact that we have a pull-up and a pull-down network is designed for power efficiency. The idea is that because transistors, MOSFET transistors, have a very high off resistance. So when they're turned off, they don't conduct very well at all. Their resistance is on the order of mega ohms when they're off. And so if you have these complementary pull-up, pull-down networks, and if you wire it up so only one of them was on at a time, it basically means that you'll have very little leakage because the output will be connected to either VDD or ground, right? But the other side will be turned off, so there won't be any. There'll be very low leakage through the gate from its power supply to its ground, right? So that's good. You want that. Now it turns out that that's only the case if you're not switching. If you're switching the gate, in other words, if the gate is changing its output from 0 to 1 or 1 to 0, yeah, then you've got an issue because there's going to be a period of time when you will get leakage during the transition. You'll have some time when both of these guys are on as you're transitioning the output, and that's called that's dynamic power consumption, and yeah, that's a problem. But static power consumption with CMOS is very low, and that's one thing that's the reason why everything has kind of gone that way. There have been other logic families developed, but CMOS has been the most successful. Now you might say, well, why is the PMOS in the pull up and the nMOS in the pull down? Well, remember, it's not hard to figure out. Like if you think back what I said, when the transistor is on, the gate is not relative, the gate voltage, right, which is fundamental, the capacitance and accumulating charge on the gate and its ability to serve as a capacitor is really what determines the functionality of these transistors. The problem is that when the transistor turns on, the bottom plate of the capacitor is no longer the body of the transistor. It's actually the average voltage of the source and drain, because you got the channel. Once that channel is established, you basically don't really have a bulk anymore. You kind of decouple the channel away from the bulk, the body of the transistor, the substrate. And so obviously, because NMOS has a grounded substrate, you want to try to keep the source and drain around the ground, right? You want to keep their voltage low, because otherwise, if you've got high voltage coming through the source and drain, that's pretty much going to pinch off your gate. It's going to cripple the gate. It's going to cripple the capacitor that forms the gate. So that's why you need to have the NMOS source and drain terminals need to be in this pull down network. They got to be closer to ground. Likewise, the PMOS, because its gate is supposedly sensitive to negative voltage, right, lower than the bulk, you want its source and drain to be closer here to VDD. So you want to have the PMOS in the pull up and the NMOS in the pull down. And so as a result of that, you end up with this thing where in every CMOS gate, anytime the output is going to be 0, you need to have at least one of your inputs has to be 1, because you need to have at least one of the inputs 1 so it can pull down. It can activate an NMOS, right? So if you look at the truth table, any row in the truth table that has a 0 has to have at least one of the inputs has to be 1. Right? Likewise, any row of the truth table that has a 1 in it has to have at least one of the inputs has to be 0 to activate the PMOS and the pull-up network. So, for example, so let's take a look at an inverter. So an inverter is nice and simple because it just has one input, and thus it has 2 transistors, and they're both kind of just mirror image one another, right? So the input comes in, it connects to the gates of both transistors. The output is connected to the middle where they join. And then if A is 0, it activates it turns on the PMOS, pulls Y up to VDD. So 0 gives you a 1 output. And then if your input is 1, it activates the NMOS and pulls the output down to ground, right? So that's nice and simple. However, if you want to do something with more than one input, like say a 2-input NAND gate, so in this case, you would arrange the pull-up transistors to be in series, and the pull-down transistors would be the pull-up transistors would be in parallel, rather, right? The P1 and P2 are in parallel, and the pull-down transistors are in series. And what that does is it basically sets it up to where if either A or B is 0, it will activate one or the other, or both, the pull-up transistors, right? Because they're in series. So you only have to have P1 turned on or P2 turned on or both turned on in order to pull Y up to VDD, because only one of these 2 PMOSs needs to be turned on because they're in parallel. As long as one of them's on, you'll have a pull-up. But because the NMOSs are in series, they both have to be turned on in order to pull the output down. So the only way to get a 0 output out of this guy is to have A and B set to 1. And that way, both of the NMOSs are on. That creates a path from the output to ground. And of course, if those are both 1, then that likewise means that both of the PMOSs are off. So the only way to get a 0 is to have A and B turned on, 1, 1. But if you have any other combination of A and B, if either A or B or both, which are the first 3 rows of the truth table, are set to 0, then that will turn one or both of the pull-up transistors on, and it will turn off at least one of the pull-down transistors, which are in series. So that's a NAND gate. Now that kind of stinks because you might be thinking, well, I don't want a NAND gate, I want an AND gate. Yeah, you can't do an AND gate. It's impossible, because an AND gate would have a 1 output if both inputs are 1, which is impossible because you can't have a 1 output if both inputs are 1, because there would be no way to turn on any of the PMOSs. There'd be no way to pull up. Likewise, an AND would be a 0 if both inputs are 0. But again, that's impossible because if both inputs are 0, there's no way to turn on one of the nMOS transistors to pull it down. So as a result, the CMOS logic has that limitation. You could build any gate you want as long as you have at least one input that's set to 1 when you're pulling down, and at least one input has to be 0 when you're pulling up. That's the only rule. And then you can scale this up. You can have, like, for example, a 3-input gate is possible, or you can, but in this case, of course, if this is a NOR gate, for instance, the pull up would be in series, the pull down would be in parallel, and there'd be 3 transistors involved, right? So the NOR gate would have A, B, and C connected to 3 PMOSs in the pull up. So in order for the output of the NOR to be pulled up, you'd have to have 0, 0, 0 for A, B, and C. And if you have any 1s in there at all, it'll cut off this pull up and it'll turn on the pull down, because the pull down has 3 transistors in parallel. If any one of those is activated, meaning if any one of the inputs is a 1, you'll pull the output down to ground. Now, if you really want an AND gate, you can build an AND gate, but you have to build it as 2 CMOS gates. So you can do a NAND and then followed by an inverter, which would require 4 transistors for the NAND and another 2. So this would be a 6-transistor structure. But you could do it. It would have, it would be 2 gates connected in series, as opposed to you wouldn't be able to build an AND gate as a single CMOS gate, as a single pull up and pull down. You need 2 sets of pull up and pull down networks to do that. Okay. So that's CMOS logic. Let's talk a little bit more about the semiconductor physics. Now you might say, well, why are we talking about this? Because this is what determines the performance and the power consumption of a chip. So it's important to understand what factors are determining your performance, when you're designing a system, obviously. So MOSFET gates are pretty neat. I kind of alluded to this earlier, but if this is a let's see, this would be this is an nMOS. So in this case, what I'm showing here in this slide, I'm not showing the source and drain. I'm not showing the diffusion areas. I'm just showing the channel. So if you're just looking at the channel, what is the channel here? Well, the body is PMOS. That means this is an N-type transistor. And so if I have, if the voltage of the gate is negative or 0, right? Then this is called accumulation mode. It means that you're basically just attracting, in the channel, you're just going to be attracting the holes. But if you start to raise the voltage of the gate, now initially, as I mentioned, the voltage is going to be the voltage of the gate minus the voltage of the body, which is grounded, right? And as you raise that up, you'll raise it from 0 all the way up until just before you hit the threshold voltage. Now what that'll do is that'll start moving the holes downward away from the channel, and that's called depletion mode. That creates a depletion in the channel. It's no charge carriers at all. Now the voltage, the threshold voltage, depends on the doping, how much you dope, and it also depends on the oxide thickness. However, most modern semiconductor processes generally have a threshold, like I said, of about 0.7 volts. That's the magic number. So anything that is less than 0.7 will put you either in accumulation mode or depletion mode, but it won't turn the transistor on at all. You'll still basically have zero conduction or very little between the source and drain. I mean, it's not zero, but it's like 10 mega ohms or something like that. There's essentially no way to get, not very much current will flow at all through the channel. However, once you exceed the threshold voltage, this is where things get a little crazy. So once the voltage of the gate is greater than the threshold, you end up with a channel. And the channel is this inversion region. It's basically the minority charge carriers collect. And then the channel becomes decoupled from the body. And instead, it becomes electrically connected to the source and the drain on either side. So the voltage of the channel becomes the average voltage of the gate to source potential minus the gate to drain potential, or the difference of those minus divided by 2. And so just you keep that in mind. So now the problem is that once that works fine until the voltage potential between the source and drain start to become too high. And once that happens, the transistor, the channel will get killed. It'll get pinched off. So what that ends up doing is it creates 3 modes for a transistor. There's cutoff mode, where the transistor's off. Your voltage of your gate is less. Voltage of the gate versus the body is less than the threshold. That's cutoff mode. And then once you turn the transistor on, you get it above. You get the gate over the threshold. You go into a linear mode. Linear mode just means that the amount of current that you pass through the transistor from drain to source, in the case of an nMOS, is going to rise linearly with the voltage of the source to drain voltage. Okay. Now you might say, okay, well that's how a resistor works, basically, right? I mean, a resistor, you raise the voltage and increase the voltage, increase the current. Right. That's right. It's like a resistor. However, once the voltage difference between the source and drain grows high enough, then you enter saturation mode, and then the transistor stops acting like a resistor, because the amount of current that goes through the transistor will stop growing as you increase the voltage potential between the source and drain. That's called saturation mode. And at that point, the transistor becomes a current source, meaning that it's a fixed current going through, irrespective of the voltage. It becomes a constant current source, which you might remember from when you took 221. You guys might have had a current source in your circuit. You might have wondered what a current source was. I mean, at least I wondered that. I'm like, well, how do I make, like, where do I buy a current source, right? Because if I get a battery, that's a voltage source, right? Well, this is an example of how you would make a current source. Is if you saturate one of these MOSFET transistors, it ends up providing a fixed amount of current. Okay, so let's look a little bit more closely at how that works. So this is the cutoff. So this is a nMOS transistor. Most of these examples, by the way, are nMOS, because the PMOS is like I said, it's like negative. Got a negative voltage for the threshold, so it's a little bit harder to. I think nMOS is a little more clear when you use that as an example. So so you've got the nMOS in cutoff mode, and basically the voltage in this case from gate to source is 0. And I mentioned that with the nMOS, you're typically going to have at least, well, not always. These sources and drains, when you build the pull down network, are going to be close to be grounded anyway. So the voltage of the gate is going to be 0. That's cutoff. Then once you hit the threshold, so once the gate to source voltage is greater than the threshold, you build the channel. right? You get a channel in there. You get a channel running through the source and drain, which are the minority charge carriers. And if you increase the source drain voltage, then the current will also increase, right? So it becomes a resistor, essentially. The current increases with the voltage between the drain and source. And then with an nMOS, the current is flowing from the drain to the source. It's the opposite with PMOS, but with an nMOS, the convention is drain to source. Current increases with the voltage between the drain and source. Now the problem is once the voltage between between the two terminals, the two main terminals, the gate and the drain and the source rather, once that gets to a certain point, then the voltage between the gate and the source, remember I said in an nMOS the source side is the lower voltage side. That may be greater than the threshold, right? But the problem is the higher side, the drain, the gate and the drain voltage, gate to drain, ends up becoming less than the threshold. Why? Because the drain is so high, the voltage of the drain is so high that the difference between the gate and the drain is no longer hitting the threshold, right? So it pinches off the channel. Now notice how it's drawn as kind of a triangle. Why is it a triangle? It's a triangle because you have these, the gate and source is still good. Gate over source, still enough to put these charge carriers on the source side. But the gate to drain voltage is low because the drain's so high. And that actually will start to bring the gate to drain will no longer be at the, it'll start to be less than the threshold. So you end up with this kind of pinch off thing here. Now that doesn't mean that it turns the transistor off. It just means that the amount of current that can flow you can't have any more current. The total amount of current is going to be stopped, right? Now that current, by the way, the amount of current that it stops at depends on the width. So if you have a transistor with a larger width, now you might say, wait a minute, what was the width and length again? The length is the distance between the source and drain. You want that to be minimal, right? Small as possible. But the width is the dimension you don't see. It's like the kind of the third dimension, like if you push back through the monitor there. That's the width, right? And the more width you have, the more current will flow when the transistor is in saturation mode, which means that the transistor will be able to switch a higher load faster. So if the transistor has a load, like you have a gate, for instance, and that gate is connected to a bunch of other gates, it has a fan out, right? You've got, or a long wire, for instance, or a pin that goes off chip, for instance, it's connecting to an SPI bus. And so you got a lot of metal. You got the gate driving a lot of metal, which means a lot of capacitance. If you have a bigger transistor here, if your width is bigger, if you have a wider transistor, then you can get more current when it saturates, and that will cause the load capacitors, whoever you're trying to drive, to charge or discharge faster. So if you have a basically, if you want a driver, you want a more powerful driver, you need a wider transistor. Okay, but anyway, okay, so there's a couple things here. In order to figure out how these transistors perform, you have to start out and look at the current voltage relationship. So you want to know how much current is going to go through the transistor as a function of what? Well, as a function of several things. As a function of the gate voltage, as a function of the source and drain voltage, as a function of the width. Remember I told you the width matters, the size of the transistor, the geometry, that matters, right? Of the oxide thickness, and anything else? I guess that's it. So basically, you want the current as a function of everything else, right? The current between the source and drain. So to calculate that, the equation is, for a MOSFET, the equation is the amount of current is the charge, which is Q, the amount of charge on the channel, divided by the amount of time it takes the carriers to traverse the channel. That's how long it physically takes the electrons or the holes, depending on what kind of transistor it is, to move across the channel's length from the source to drain. You might say, really? It's just the time, the travel time? Yeah, just the travel time, the physical amount of time it takes to move the charge carriers. All right. So let's start out with the numerator in this equation. The numerator is the charge. What is charge? What does that mean? I don't know if you guys ever talked about charge, probably maybe in physics. Charge is actually the capacitance times the voltage. What's the voltage? Well, I mentioned that the voltage of the channel is the average of the voltage. The gate voltage is the average voltage along the gate between the source and drain. So you can calculate it as, for example, the gate. It's the average. It's the gate. It's the gate source minus the gate drain divided by 2. But you could rewrite that as simply the gate source minus the gate source minus the source drain divided by 2. The gate to channel. The voltage of the channel, which is what you want, gate versus channel, is equivalent to the gate versus the source minus the source versus the drain divided by 2. So this is just, you arrive at this just by rewriting the math, or rewriting the expression to calculate the average channel voltage between the source and drain. Okay, so you then take the capacitance of the gate, and then you have to, the voltage of the gate effectively is the voltage of the gate versus the channel, which I showed up above, but you have to subtract the threshold voltage because that doesn't count. You have to get above the threshold voltage before you start accumulating charge on the channel. And I never really entirely understood why that's the case, but you have to get above that threshold voltage before you start accumulating charge on the channel with a MOSFET. Okay, so then the charge of the channel is the capacitance of the gate multiplied by basically the gate voltage minus the threshold voltage. That's all this is. Okay, what about the capacitance of the gate? The capacitance of the gate is the dielectric constant of the oxide. This is just a capacitor equation. Essentially, it's it's usually actually called permittivity. The permittivity of the oxide. What's oxide? Well, that's just the middle part of the gate. It's glass, silicon dioxide. Silicon dioxide is a great thing to use for the dielectric in a capacitor, but it has a good permittivity, and that's what that epsilon is, the permittivity of the oxide. So that depends on the material, obviously, but we're specifically concerned with the oxide. And then you multiply that against the area of the gate, which is the width times the length, and you divide that by the thickness of the oxide. So the permittivity of silicon dioxide is 3.9 times epsilon 0. Epsilon 0 is the permittivity of a vacuum. If you have like literally just what is the permittivity of empty space? That's totally empty, like empty of everything, total vacuum. So the permittivity of silicon dioxide is 3.9 times the permittivity of a vacuum. And the permittivity of a vacuum is 8.85 times 10 to the negative 14th farads per centimeter. It's not really that important to know that. It's just that's a constant. Okay, so So you got the capacitance of the oxide. You can separate that out from the area of the gate, and then you can kind of rewrite this as the capacitance of the gate as the capacitance of the oxide multiplied by the area of the gate. That's just a way to rewrite that. Okay, and then if you go back to the original charge of the channel, is you go back to what we had over here in the left column, and you substitute in this for capacitance of the gate. So you just take that, you stick it over on the left, and the right side is the same as it is down there. Okay, now we have to figure out the carrier time. And this part is a little wild, but it's important to know this, and I'll point out why this is important in a minute. So we need to know the velocity of the carriers. How fast do they move? You know, I'd say, oh, well, they're carriers, right? They move at the speed of light, don't they? No, they don't. Slower, much slower. The velocity is mu, which is the carrier mobility, and that depends on what type of carrier, if you're electrons or holes, and you know, in the semiconductor itself that you're starting with, and you multiply that by the electric field. The electric field is literally just the voltage between the drain and source divided by L, the channel length. That's actually, it sounds complicated, but it's actually not. And the velocity is so the velocity is actually mu is the mobility multiplied by E, so which we calculate here. So it's mu times VDS over L. And then the carrier time is therefore going to be L divided by the length over the velocity. The length of the channel divided by the velocity. Well, that makes sense, right? That's just distance equals time times velocity, right? That's all that is. That's literally just distance equals the time times the velocity, but rewritten where you're solving for the time. And so then if you take this and you take the velocity and you put that into velocity, it ends up becoming the L squared divided by mu v ds. Now you might say, well, what are you getting at here? Okay, what I'm getting at is, notice that the carrier time is, first of all, notice that the carrier time, we want the carrier time to be small, because the smaller the carrier time is, the more current we get. We want more current, right? Notice how the carrier time, right, we want this to be small, it's in the denominator, right? So we can make the current bigger. Notice that L squared is in here, right? What is that? What is the implication of that? Well, the implication is if you shrink L, you get a big impact from that, right? Now you're thinking, wait a minute, why is Intel so embarrassed because they can't get the 14 nanometer process off the ground? Oh, they're being humiliated by TSMC. Oh, Samsung is humiliating. Oh, the GPU is already 11 nanometers. What is Intel doing? What is wrong with them? We got to get that down. Where's the 14 nanometer process, Intel? What's wrong with you? Well, the reason why there's such pressure on them is because of this, L squared. The channel length is wildly important for the performance of the transistors. L squared. So that's important. We got to get that down. Intel's got to get the 14 nanometer process up and running. They got to, because look at how important this L is, this L term. Okay, so right. So basically, this was supposed to animate. Sorry. So if you go back and you calculate the whole thing, what you can do is you have basically two parts of this equation. You've got the voltage gate to source, voltage of the threshold, which is basically fixed. That doesn't change with Moore's law. And then the voltage ds over 2. These are, voltages that are kind of dynamic values that change, and then, well, of course, except for the threshold, which is a constant. When it comes to this, the The other part, though, is carrier mobility, oxide. Those generally don't change too much, but the width and length change, right? So the length you can't change, that's fixed, but the width you can. So as a designer, you can make bigger, you can make wider transistors, and you can get more current to flow through them. And if you get more current to flow through them, they become more powerful. And more powerful means that they can switch larger loads faster. Of course, the problem is that the transistors will, when they saturate, they're limited in how much current, but that current depends on, it depends on ultimately the most current you can pass through depends on the width, the size. Okay, so it also depends on the gate voltage too, though, as we'll get to. So it's a little bit more complicated. Okay, so then now I'm not going to go into all the details for this part, but basically what I just derived was the current that flows through the transistor in the linear region, right? The saturation region is very highly related to that. The only difference, in order to derive the saturation equation, it's basically you just take the voltage, drain source, and you see this term right here, voltage drain source, and you substitute for that VGS minus VT, and that'll give you the saturation. I'm not going to get into that, but the important thing to understand here is two things. One is that the length of the channel makes a big difference in terms of the switching time and the amount of current, and also this beta term, the beta is the value that you can manipulate when you design your chip by making wider transistors if you want to. Now, the other thing you have to keep in mind, and this is one final, this is kind of important. Remember that mu term, that was the carrier mobility. So that was, this mu is part of the velocity. So we needed carrier time, which was a function of velocity. The velocity was a function of the electric field, which had to do with the voltage and the length, but also had to do with mu, the mobility. That's how mobile the charge carriers. Well, it turns out that the mobility of the carriers in N is 2 to 3 times that of P, right? So N-type silicon, which has the mobility of the charge carriers in N-type, is 2 to 3 times more than P-type. So what that means is, in order to create a balanced gate, your PMOSs have to be at least twice the size of your nMOSs in terms of the width, twice as wide. Okay, so so for instance, then, if you look at, you can plot these IV curves. This is the DC response. So if you set the gate source voltage on an nMOS to different values, and then you scale up the drain to source voltage, and then you look at the current that flows through, you can see that depending on what gate voltage you put on, you'll reach the saturation at slightly different points. So, like, for example, if your gate voltage is 1.5, then you'll saturate at around, in this case, I don't know what technology this is in, but this is, about 1 volt, you'll saturate, right? But if your gate voltage is 1.8 volts, you'll saturate a little lower. So you can see the saturation point is when the curve kind of flattens out. The current flattens out as you increase the voltage between the drain and the source, right? In this case, the gate source is just below the threshold, and it's basically not conducting any current at all, right? So this is kind of the cutoff right here, this bottom line. And then if you look at these other lines, you're seeing both the linear region, which is when you linearly increase the the current as you increase the voltage, and then you're also seeing the cutoff, which is when it rounds off, right? So that's for the NMOS. For the PMOS, now this is where I mentioned the PMOS is usually a little weirder. Now, first of all, the gate source voltage is negative, so it's going to be 0.6 to negative 0.6 to negative 1.8 here. And also, I also mentioned to you that the source and drain are usually flipped in a PMOS. And that part, I mean, again, that's a convention. But because the source and drain are flipped, obviously the current is also negative, right? Just because you're switching the two terminals. And again, this is something though that, if you look at the actual transistor, the source and drain are symmetric. But the convention is that the current flows the opposite direction. So you've got this, negative current and the negative gate voltage here for the PMOS. Okay. All right. Okay. I'll go ahead and end it there for now. So I'll give you a little time to look at the quiz, just so you have an idea of what kind of questions to expect, and you can start working on that. And then we'll come back on Wednesday. I might be able to finish up the lecture on Wednesday, or I might have to almost finish it and kind of tie it up on Monday. So yeah, so there we go. That'll do it for today. If you have any questions, let me know. And we'll see you on Wednesday. If you see any issues with the quiz, as always, let me know as well. Thank you.